Okay, so today we are going to be going through 3.2 and 3.3, which has to do with a couple of theorems and then something called the first derivative test. So that being said, ooh, I don't know why that happened. Just keeping things interesting, guys. All right, here are the guided notes. So we have some objectives, you can read through those, and then problem set 3.1 is due, 3.2 and 3.3 are your homework, and the lecture will be linked as soon as it is finished. So part 1 is Rolle's theorem. And before we do that, we're going to recall the extreme value theorem. And the extreme value theorem was from last week's notes, and it says that a continuous function on a closed interval must have a minimum and maximum on that interval, okay? And that max and minimum further can occur at the endpoint. So that is what our extreme value theorem tells us. That moves us into Rolle's theorem, which is defined as the following. Let f be continuous on the closed interval a, b, and differentiable on the open interval a, b. If f of a is equal to f of b, then there's at least one number c in a, b such that f prime of c is equal to 0. And so that's a lot of words, but once we actually do problems with Rolle's theorem, we can kind of see that it comes down to 3 things that I've put together in this following checklist. So this is like the Rolle's theorem checklist. And so in order to apply Rolle's theorem, you have to check 3 things off. Number 1, do you have a continuous function? Okay, so you can check that by using your knowledge of functions for pre-calc. You can graph it in your calculator, you can graph it on Desmos, etc. Check point 2. Does the function have a derivative? Can you take the derivative of the function? And then check point 3, is f of a equal to f of b? So if you evaluate the function at the left endpoint a, is it equal to the function evaluated at the right endpoint b? So if we can check off all 3, then we know that there's some x value between f of a and f of b where the graph has a horizontal tangent. Reminder, we have a horizontal tangent when the derivative is equal to 0. Okay, so we have a couple of examples here. So illustrating Rolle's theorem. Let f of x equals x to the 4th minus 2x squared. Find all values of c in the interval -2 to 2 such that f prime of c equals 0. So we want to go ahead and employ our nice little checklist here, right? So the first thing, continuous. So this function is continuous because it is a polynomial. I should know this, but you can graph it in your calculator. It's continuous. Can you take the derivative? Check point 2. So f of x equals x to the 4th minus 2x squared. So therefore f prime of x equals 4x cubed minus 4x. So we have a derivative. Continuous check, derivative check. And then f of a equals f of b is our final checkpoint. So if f of x is equal to x to the 4th minus 2x squared, and our interval is -2 to 2, we want to check f of -2, which is going to be equal to -2 to the 4th minus 2 times -2 squared, which is going to be equal to 8. And then we want to check f of 2, which is our other endpoint. That's going to be equal to 2 to the 4th minus 2 times 2 squared, and that is also going to be equal to 8. So f of a does equal f of b. So since our checklist is completed, then we know that there is some point in the interval between f of a and f of b where the graph has a horizontal tangent line. So a horizontal tangent line takes place when the derivative is equal to 0. So we're going to focus on our derivative and set it equal to 0. So 4x cubed minus 4x equals 0. I'm going to go ahead and erase this work here so I have some room to write. And what I'm going to do to solve for x here is I'm going to factor out my greatest common factor, which is going to be 4x. So when I factor out 4x, I get 4x times x squared minus 1 equals 0. And then I can factor x squared minus 1 into x plus 1 times x minus 1. And that's equal to 0. And then since I have things multiplied together and equal to 0, you might have forgotten this, but because of the 0 factor property, we can set each thing individually equal to 0. So 4x equals 0, x equals 0. x plus 1 equals 0, x equals -1. X minus 1 equals 0, x equals 1. So therefore, we know that the derivative is going to be equal at x equals 0 and plus or minus 1. So we know that the derivative will be equal to 0 at 3 separate points throughout our function. All right, example 2. Find the two x-intercepts of f of x equals x squared minus 3x plus 2 and show that f prime of x equals 0 at some point between the two intercepts. So here we want to first find the two x-intercepts of our function. So to do that, since we have a quadratic function, we are going to factor and set it equal to 0. So f of x equals x squared minus 3x plus 2. So when we factor that bad boy, we're going to get f of x is equal to x minus 1 times x plus 2. Set that equal to 0. We're going to get x equals 1 and x equals -2 for the x-intercepts. So the first part of this problem was to find the two x-intercepts, which we have done. And then the second point is to say, show that f prime of x equals 0 at some point between the two intercepts. So why did we find those two intercepts? Well, we need to show that f prime of x equals 0 at some point between those two. So that means Rolle's theorem. And further, that the interval for our Rolle's theorem problem is going to be 1 to -2, because that is between the two intercepts that we found. So checkpoint 1, continuous. We have a quadratic function, so we know the answer is yes. This is a nice old parabola, which will be continuous. Checkpoint 2, derivative. If f of x equals x squared minus 3x plus 2, then f prime of x equals 2x minus 3. So we do have a derivative, and then f of a equals f of b. Well, we need to check that f of 1 is equal to f of -2. And if we plug f of 1 and -2 into our original function, it turns out that this does actually work. So f of a is equal to f of b. I will let you guys work on that algebra, work out that algebra on your own. And now we need to show that the derivative is, and since we have met all three of our checkpoints, we know that the derivative will equal 0 at some point between those two. And now we just need to find that point by setting our derivative equal to 0. So 2x minus 3 equals 0, 2x equals 3, x equals 3/2. So we have shown by completing our Rolle's theorem checklist that there will be a point where the derivative equals 0, and further that that's going to be at x equals 3/2. So that's kind of a couple examples about how Rolle's theorem will be used. All right, part 2 is the mean value theorem, defined as if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then there exists a number c in a, b, such that f prime of c, so the derivative evaluated at point c, is equal to f of b minus f of a over b minus a. So this one can kind of be interpreted in different terms. So this basically is saying that there exists a tangent line that is parallel to the secant line. Okay, so reminder of tangent line versus secant line. A tangent line touches a curve at one point, right? So if we have like a curve here, a tangent line touches at one point. So this would be tangent. Versus a secant line touches at 2 points. So like this would be secant. Okay, and so this is telling us that there's a point where a tangent line is parallel to a secant line. And remember that instantaneous rate of change is derivative, deals with tangent lines. Average rate of change is rate of change, deals with secant lines. So this is telling us that there's some point where the instantaneous rate of change is equal to the average rate of change. So example 1, finding a tangent line. Given that f of x is equal to 5 minus 4 over x, find all values of c on the interval 1, 4, such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Okay, So the first thing we're going to do is find our derivative. So f prime of x. The derivative of 5 is going to be 0. So we're finding the derivative of -4 over x, which we can rewrite as -4x to the -1. So that's going to be equal to 4x to the -2, which can be rewritten as 4 over x squared. Okay. And then we want to evaluate f of 4 minus f of 1 over 4 minus 1. So f of 4 is going to be equal to 4. Hopefully you can plug that in and figure that out on your own. F of 1 is going to be equal to 1. Again, hopefully you can plug that in and figure it out on your own. So f of 4 minus f of 1 over 4 minus 1 is going to actually equal 4 minus 1 over 4 minus 1, which is equal to 3 over 3, which is equal to 1. And so now f prime of c equals 1 is what mean value theorem tells us. So f prime of c is equal to 1. All right, so that means that 4 over x squared equals 1. I'm going to multiply my x squared out of the denominator. Then I get 4 equals x squared. So that means I know that x is equal to plus or minus 2. Okay, so I have found two values of c on an interval such that f prime of c is equal to such that my average rate of change is equal to my instantaneous rate of change. So these mean value theorem problems kind of seem like weird and confusing, but take them one step at a time, right? So first we want to find, a derivative, and then we want to evaluate our derivative at a certain point. So to find that point, we plug in some values to our initial function. We find out that that's 1. We set our derivative equal to 1, and then just solve for x. All right, and I'm going to save this second example for class time in the interest of not making a 10-year-long video. All right, part 3, increasing and decreasing functions. So you can read through those definitions, and just a quick side note on these notes, like I know that by watching the videos and just hearing me like throw all these definitions at you, you're not going to retain it. You need to take the time to go back through notes, especially after class time when we've done more problems together and I've explained more, and go back through the notes and make sure, okay, does this really register? Is this actually making sense for me? You need to spend that time outside of class, especially in AP Calculus, especially with 45-minute class periods. But anyway, I will get off that soapbox and continue to increasing and decreasing functions. Basically, as x moves to the right, so as we go this way, if a graph is moving up, then it's increasing, and the graph is moving down, it's decreasing. So very basic definition there. It's written in fancy math terms above right here, but you can see if a function is increasing or decreasing. So now we move on to a theorem, a test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval and differentiable on the open interval ab. And if if your derivative is greater than 0, then f is increasing. If your derivative is less than 0, then f is decreasing. And if your derivative is equal to 0, then your function is constant. Okay, so we are using the derivative and the sign of the derivative to tell us something about the function. Okay, so if you memorize these steps, this is how you solve these type of problems, right? So locate the critical numbers, use these to determine the test interval, determine the sign of f prime of x at one test value in each of the intervals, and use the above theorem to determine if f is increasing or decreasing on each interval. So, for example, number 1, find the open intervals on which f of x equals x cubed minus 3/2 x squared is increasing or decreasing. So step 1 is to find the critical numbers. Critical numbers are where the derivative equals 0 or doesn't exist. So f prime of x for this function is going to be equal to 3x squared minus 3x. We're going to factor out a 3x. We're going to have x minus 1, 3x times x minus 1 equals 0, x equals 0, and x equals 1. Okay, so use these to determine each test interval. So we know that the function f of x equals x cubed minus 3/2 x squared exists from -infinity to infinity. So then our intervals are going to be from wherever the function starts to our first test point to second test point to, if there's more test points, and then like your last test point to the end of your interval. So for example, in this problem, it's going to be -infinity to 0, 0 to 1, and 1 to positive infinity. So there's our interval. And we can actually draw this in a nice little table. So I'm going to erase all my work. Hopefully you understand how to take that derivative, etc. Interval, test value, sign, conclusion. So my first interval, negative infinity to 0, 0 to 1, and 1 to infinity. And you may have many intervals depending on how many critical numbers you have and what your interval is. All right, test value. I can literally pick any value as my test value as long as it's within my interval. So between negative infinity and 0, I'm going to pick x equals negative 1 because that's an easy value. The sign refers to the sign of the derivative. So I'm going to be evaluating f prime of negative 1. Okay, so f prime of x, reminder, is equal to 3x squared minus 3x. If I plug in negative 1, I get a positive 6. And so since it is positive, I can conclude that f prime of x greater than 0, therefore my function is increasing, okay? Between 0 and 1, I'm going to pick x is equal to 1/2. When I plug in 1/2 to my derivative, f prime of 1/2 is equal to negative 3/4. Since that is f prime of x less than 0, I can conclude that my function is decreasing. And then finally, we have 1 to infinity. I'm going to choose x equals 2 as my test value. F prime of 2, when I plug that into my derivative, I get positive 6. So I'm back to increasing. Okay, and so the open intervals on which f of x equals x cubed minus 3/2 x squared is increasing is going to be negative infinity to 0 and 1 to infinity, and decreasing on 0 to 1, which I can see from my nice little table. So as a whole, this is actually not that hard at all. You just have to be comfortable with taking derivatives and finding critical numbers and knowing the interval of your given function. Okay, so this takes us to part 4, which is the first derivative test. And the first derivative test is basically an extension of this increasing and decreasing function. And it just tells us that if c is a critical number and f is continuous, blah, 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 read all that, that if f prime of x changes from negative to positive, then f has a relative minimum. If f prime of x changes from positive to negative, then f has a relative maximum. And if f prime of x is positive on both sides of c or negative on both sides of c, then f of c has neither a relative minimum or a relative maximum. So in this above example, which we just did, now we know that the first derivative test would tell us that since our function changes from increasing to decreasing right here, that we know that f prime of 0 is going to be a place where there is a relative, it changes from increasing to decreasing, so it changes from positive to negative. So that means we have a relative maximum. So we know that f prime of 0 will be a relative max. And you can think of it as, we know that because it's changing from increasing to decreasing. So that's going to show us increasing to decreasing. Oh, that's going to be maximum. Also, we can look at the sign of our derivative, which is changing from positive to negative, positive 6 to negative 3/4. So that's going to be relative max. And then from here, we know that f prime of 1. So we know that, actually, we know that 0 is going to be a relative max. And that 1 is going to be a relative min, because our derivative is changing from negative to positive, and our function, therefore, is changing from decreasing to increasing. We can see relative min. So there's a bunch of practice problems, so you can go ahead and try to work through those. And what we are going to do first thing in class is go over those example problems together. So thank you for watching. Sorry, this was kind of a long video. Maybe you can watch it on 2 times speed or something. I know I talk fast though. Yeah, see you in class.